called light reactions. You have to have light present for them to work. Okay, there ain't no way chlorophyll is going to work unless you have light shining on it. Does that make sense to you? All right. And sometimes that's very interesting to figure out, you know. I've worked in a lab before. During the day shift, we got reactions to run. And night shift, the guys couldn't get the reactions to run. And finally, we got figured out what the problem was, is it was the light shining through the window, you know. And a lot of the night shift guys where I was at was international students. They were from China and so forth. And a lot of times they decided to work at night where they'd be with their kids during the day. And they were good chemists, but they couldn't get the reactions to run. And I thought, man, this is silly. These guys don't play. Well, I took off one day and worked with them at nighttime, and guess what? The reaction did not run at night. And the reason is because there wasn't no daylight coming in through that window. Now, that was a good thing for us, right? We got to put that in a paper. That was a good discovery and all this and that. Now, sometimes they put reaction conditions. In other words, 100 degrees centigrade, like a temperature. You know, the reaction would work at that temperature. Sometimes they'll put times, like 3D, you know, for 3 days or 3 hours or something like that. And a very common one for chemists is 2 days, 3 days, 24 hours, 8 hours, and so forth. And a lot of people think that there's something magical about that. And sometimes there is something magical about it. But a lot of times, 12 hours means I started the reaction at 7 o'clock at night. I watched it for 30 minutes to be sure nothing was going to happen. And I went home and slept. I came back at 7 o'clock in the morning and turned it off. So we just write down, hey, that was 12 hours. Same way with this right here. This is a long weekend. Somebody put this on Friday and come back on Monday. All right? And they just write down what they did. And it tends to work. Now, it could work at a lesser time and so forth. Okay. Now, the next thing we got to do, well, before I do that, let me put this up here. Let's say that we got C3H8. This is called propane. If we burn that, what are going to be the two products? CO2 and water. Now, I want you to raise your hand if I give you a test if you're going to put something other than CO2 and water right here. You will. You will. You'll put some crap. Carbon monoxide. You'll put O3, ozone. You make an ozone. And you'll put all kind of weird stuff. But it's always CO2 and water. That's the reason I give it to you as this first one right here, right? Because it works all the time. Let me do one more. Let me do, no, I don't want to do octane yet. Let me do butane. C4H10 plus oxygen, right? Like a butane lighter if you smoke the cigarettes. You know, the plastic ones that you buy. What is that going to give you? CO2 and water, man. You guys are picking up on it.
We don't see the water.
What's that now?
When they smoke, they don't see the water, do they?
No, you can't see the water. But one of the ways you can see it is, and maybe, John, do you use one of those lighters or do you use a Zippo? And I wonder if there's any glassware here. If there's not, maybe I'll run down and get it. He probably leaves these closed up. Ah, here's a piece of glass. Right here. Ta-da! All right, so John here has got a wonderful habit of smoking, right? Now, who asked me if they could see this? You ready? You ready to watch this? You see that?
Mm-hmm.
There's your water coming out. All right. You want to see it? You see that water vapor?
Yeah.
All right. It's not coming from inside the glass. It's coming straight off this ladder. Okay? Now, whenever it gets hot enough, you're not going to see that water vapor on there anymore. Why? Because the temperature of this thing is what? Over 100 degrees, right? So you won't see it. So that's where the CO2 and water is coming from. All right? And naturally, you can't see the CO2. All right. What are we doing? I don't even know what we're doing. Oh, okay, we're going to balance. Now, there's this law of conservation of mass that says this: matter cannot be created nor destroyed in a chemical system. Not in a nuclear reactor, not in some kind of weird thing going on at Oak Ridge. I'm talking about in a chemical system. You just cannot create matter. All right? You just can't lose matter. You have to have what's called a mass balance or a material balance. Now I'm going to draw little blanks up here. And you can only put numbers in those little blanks. And they are called coefficients. That means something before the chemical. All right, and your book calls these stoichiometric coefficients. So that's the big $14 word for them. And basically what you have to do is this. If you've got 18 oxygens on the left, you have to have 18 oxygens on the right. And there's no way about that. And there's nothing special about 18. If you have 48.3 oxygens over here, you got to have 48.3 on this side. There's nothing special about it. It's got to equal. So let's look at this one. We got one carbon up here and one carbon here. That's just Jim Dandy. We got 4 hydrogens here. So what do I need to do to make this number 4? Put a 2 there, right? Now some joker is going to erase this right here and put a 4 there and call that H4O. Now why would you not want to do that? That's not water. The first rule in working any chemical system is you have to have an equation that is reasonable. H4O is not reasonable. That ain't going to work. Okay? So now I got 4 hydrogens here. Look here about oxygens. How many oxygens have I got on my right-hand side total? Well, I've got 2 here. And how many here?
6.
Huh? 6. 6 oxygens? Well, I've got 2 times 1, which is 2 here. And how many do I have here? 2. So that's 4. So how many have I got to have on the left-hand side? 4. So what have I got to do? Are we balanced? Yeah, we are. So we are now something that is called mass balanced. Everything that we write, I mean, this is simple, people, but it's hard because you got to practice it. If I write down oxygen here, I have 4. If I write down oxygen here, I have what? 2 plus another 2 is 4. Do you see how those numbers have to jive? Same way with carbon. There's 1 carbon here. There's 1 carbon here. Hydrogens. There's 4 hydrogens here. There has to be 2 times 2, which is 4 hydrogens here. Everything has to equal. There's nothing magic about the numbers, only that they have to be equal. Is there anyone that's confused on that? Okay, let's do another one. All right. Now, C3H8. Well, how many carbons we got over there? 3. How many we got to have over here? 3. If there's 3 carbons here, how many we got to have over here? 3. All right. Is that why I want to put the number in front, or do I want to put the number down in here? In front. Okay. How about hydrogens? How many we got over there? 8. How many we got to have over here?
8.
So what have I got to put here? A 4, right? Because 4 times 2 is 8. You together with me? Okay, what's left? Oxygen. All right, let's do a right-handed side count. 3 times 2 is, plus 4 times 1 is, so that's 10 total on my right-hand side of the equation, right? So what number do I have to put here? All right, let me ask you this. From a chemical perspective, which one burns more efficiently? Methane or propane? Propane does. For every 1 mole of propane,